Hey physics students, this is Mr. Galoya coming at you. Hey, I wanted to try to work a few more problems, practice problems for you. I've got this kind of packet here, and I think I'll try to zoom in with this other webcam and maybe run through a couple more practice problems, and then have you guys try a couple off of this packet. I think there's 4 total. So that's what I'm going to try to do. Okay, so I got this kind of worksheet packet here in front of us. We said a type 1 parabola, type 1 trajectory, basically the object's going to be above the ground. It's going to be shot off kind of horizontally. Launch angle will be 0. It'll be in CV horizontally, and then it's going to be in free fall going down vertically. Hope you can kind of see that there. I know I'm kind of bouncing around there. I've got this kind of camera on my head. So basically in the x direction, we have then the CV equation. The speed doesn't change because we're at CV. And then we're going to be in free fall in the y direction going down. And the object will be getting faster and faster negatively as we go down. And we'll be in free fall. And there's that little g there. So I'd like to maybe try to work a few of these practice problems, and then maybe have you guys try a few. So as a kid, I would watch cliff diving on the Wild World of Sports. Let the height of the cliff be 44 meters, so that's going to be the altitude. And the diver runs off the cliff at 3 meters per second. So this will be our Vx. Our Vx will be 3 meters per second. And the height above the ground would be, in this case the water, would be around 44 meters. So we want to draw a parabola to show the cliff diver's motion. So I'm just going to kind of put all my work here, and hopefully you'll be able to see what I'm kind of doing. So we'll be doing something kind of like this here, and here's kind of the water, and here's kind of the cliff, and the diver is going to be running then at 3 meters per second. That's going to be our initial velocity in the x direction. And that's not going to change as we go through our trajectory here. So I'm just going to draw some horizontal velocity vectors. That's always going to be 3 meters per second. And the initial velocity in the y direction will be 0. But once the diver leaves the cliff, the diver's going to be getting faster and faster negatively as he or she's in free fall. So I've got this parabola, I've got some of the vectors drawn. So what is the acceleration vector along the parabola? Well, there's no acceleration horizontally. Vertically, then we're in free fall. So my acceleration would be negative 9.8. So my downward acceleration vector is negative 9.8 meters per second per second. Again, that would be then g. So first off then, our first numerical part of this problem really is how long will it take the diver to strike the water below? And we're getting an answer of around 3 seconds, but let's see how we might be able to get that. So we used the height then. We said our height then is 44 meters. So relative to kind of where we started, where the diver started, the diver's going to fall 44 meters below where he or she started. So I'm going to call that a negative 44 because it's a motion below where he or she started. So we can basically say the motion then, how far downward. So we could say yf minus yi will equal to viy t plus 1/2 at squared. So this is our how far equation written to denote vertical sort of motion. So this final y or position minus the initial, well, the initial position is 0 and the final is 44 meters below where he started. So this will be minus 44 meters. The initial velocity in the y then is 0. So this term goes away here for type 1 trajectories. And we're left then with 1/2 times EA, but that's what this G is. So that's going to be negative 9.8. Sorry, maybe I got off there a little bit. That'll be negative 9.8 meters per second per second times t squared. Okay, we'd like to find that time, so that's the variable that I'm isolating here. So if I just run through the algebra here, negative 44 meters equals negative 4.9 meters per second times t squared. So on my calculator, I'm just going to take negative 44, and then I'll divide that by 4.9. The two negative signs really cancel out. So we're left with t squared is 8.979, etc., etc. There's my number. And we want to then take a square root, so I'm going to take this to the half power. I'm going to get about 2.99, or the time is about 3 seconds. And that's the answer I gave you here, 3 seconds. So how long will it take the diver to reach the water? Well, that would be 3 seconds. Okay, so we've got this part. So what are the velocity vectors just before he strikes the water? So we're looking kind of at this picture here. So we know, this would be part E then. We know then in part E, he's going to be moving forward at 3 meters per second. So that's my x velocity. Downward then, he'll be traveling, we really kind of have this sort of vector velocity vector triangle that we have. And so we know downward his velocity is changing. So I'm going to take that vector here that I drew here and kind of just slide it over here to make this triangle. And so we'd like to figure out this velocity in the y direction at that time. Well, for that we'll need our how fast equation. So velocity in the y direction will be my initial velocity in the y direction plus at. That's just my how fast equation. This is my how far, this is my how fast, but again this term goes away, and we have negative 9.8 meters per second times 3 seconds, because that's the time that we want. That's basically going to be the impacting of the water. So we'll take then negative 9.8 times 3, we're left with 29.4. And that's going to be negative meters per second because it's downward. Well, we kind of know that from the arrow here, right? So that's going to be really 29.4 meters per second directed downward. So there's my two vectors here. So those are the two components of my vector, my x and my y vectors. Okay. Now we really then want to get the overall velocity vector, that's part F. That's going to be this hypotenuse. So when we watch this diver come in, this diver is going to come in at kind of some sort of hypotenuse there that's based on a Pythagorean theorem here with these two. So again, this would be part F right here. This would be the overall velocity vector. And then this would be my velocity vector angle right there. Remember, for a vector we need a magnitude and an angle. So what I've got then is this overall, which I'll call just Vx. That's going to be the square root of Vx squared plus this Vy squared. Again, that's my Pythagorean theorem, right? So I'm going to take 3 squared plus my 29.4 squared. Really, this is kind of a negative, but when we square it, it's just positive. Plus the arrow kind of shows us that, right? We want to take a square root of all that. So on my calculator, I would take 3 squared. Okay, I'm going to enter that. Plus my 29.4 squared. I'm going to add that all up together, and I get 873.36, but I got to take the square root of all that. So I'm going to take that to the half power, and I get around 29.6, somewhere around there, 29.5 meters per second, or maybe 29.6, depending on how you round it. Okay, so this represents how fast he enters the water. But we also need to get this angle, right? Well, that's a tangent idea, so tangent theta will be the opposite over the adjacent leg. Opposite over the adjacent leg. So for this one, I need to make sure your calculator is in degree mode if you're using a graphing calculator. So I want to take then second tan 29.4 divided by 3. I'm going to close my parentheses there. I'm going to click enter. I get about 84.2 degrees. And here I rounded that to 84. Now we can call that negative. So like if we're dealing with our quadrants, first, second, third, and fourth. Okay, if we're going this way, we could call that angle negative. So that he's going to be coming into the water kind of like that, right? So that's going to really then be a negative 84 degrees. All right? All right, that makes sense. We just got one more part of the problem to do. So that G part then is how far did the driver travel horizontally? This is also called the range. So really what we want off this picture is how far from the base of the cliff did he go forward? And again, he's doing CV in that direction. So we can say XF equals XI plus VXT. All right, so his XI, again, we're calling this a reference point, so that'll be 0. Vx then is 3 meters per second. Okay, 3 meters per second. And he's going to be going at 3 seconds. All right, 3 seconds was his time. So that's going to be our 9 meters. So forward he travels 9 meters. Okay, so he's going forward for 3 seconds, he's going down for 3 seconds. And we get this, when we kind of combine these ideas, we get this half of a parabola. So this first example problem is kind of done. And I'll work the second one shortly. Okay, so again, we're kind of into this packet here. Let's do another example together. This packet has 4 total problems. We're going to work a couple of these together, and then I'll have a couple for you to try on one of your assignments. And so again, we're dealing with what I call type 1 trajectories. You see a lot of this in like maybe baseball. So when my younger son was younger, when Ryan, my younger son, was younger, he played a little bit of baseball. He was a pitcher. And so he throws the baseball horizontally at 38 meters per second. Okay? So this would be a Vx, or your initial velocity in the x direction. But remember, for type 1 trajectories, really with all projectile motion, we have CV horizontally, right? So we have CV horizontally. His arm is 1.5 meters above the ground. So we could basically, as he's throwing this ball here, the ball does something kind of like this. So there's our type 1 trajectory. So we have a Vx, or Vix, okay, the initial velocity in the x direction, which is just the same as the velocity of the x throughout the trajectory, is going to then be 38 meters per second. I know I didn't draw that really big, but maybe we can show it a little bit larger here. So the initial velocity is 38 meters per second, and that doesn't change along my trajectory. Okay, so when the ball then leaves his hand, it's going to start becoming then in free fall. So it's going to get faster and faster. And that increase of that velocity is based on the acceleration due to gravity, negative 9.8 meters per second. Sorry. I'll try to keep my head steady. So he is basically 1.5 meters above the ground, or the ball will travel downward 1.5 meters. Okay, so we got our velocity vectors. We know what the acceleration vector is. We want to find out then the time it takes for the baseball to strike the ground. So that's going to, again, be based on here. So we're going to use our how far equation. So remember, our how far equation kind of looks like this. But since we're talking about vertical motion, we often will put in y symbols instead of using x symbols. And since we're in free fall, we can put that g there. Right? Does that all make sense, kids? So the baseball started at a reference point and went 1.5 meters below vertically, right? So this would be negative 1.5 meters. Initially, in the y direction, there's no velocity, right? The baseball's coming off horizontally only. So that velocity in the y direction is 0. So this term goes away. So that's going to be 1/2 negative 9.8 meters per second t squared. All right, does that all make sense? Now we just have to figure out what t is equal to. So negative 1.5 meters will be equal to negative 4.9 meters per second. So on a calculator, I can say, okay, well, 1.5 divided by 4.9, okay, I get 0.306. My negative signs cancel. Then I can take a square root of that, and I get then around 0.55. So the time is about a little bit more than half of a second. All right, and that's kind of what we're getting here, 0.55. All right, so the baseball is going to fall 0.55 seconds. It's going to travel forward that much time also. Okay, so we got that one done. Now, right before the ball strikes the ground, it's going to have then horizontal velocity. We know that's going to be 38 meters per second. And it's going to be traveling downward with some velocity in the y direction. We're not sure what that is, but we're going to find it. But what I can do is clone this or slide this vector over. And then we're creating then again a velocity triangle. And the true velocity of the ball really represents the Pythagorean theorem of those two. Well, how are we going to get this Vy? Well, that's basically based on the how fast equation. So the VIY again is 0. The A would be negative 9.8 meters per second. We know the ball is going to be then going to hit the ground right at 0.55 seconds. So we're going to take the acceleration g times the time. So we're going to take 9.8 times our 0.55. And that's going to be 5.39. Or around 5.4. Now we know that's negative because it's directed downward. But we can use the arrow. Remember that this really is not a negative number. It's really the vector, the magnitude of the vector is the true value of a velocity. So we can say 5.4 meters per second downward. So those are what we call the two components, the velocity components. Now what we can do on part E, we can basically get this overall velocity vector, and that's going to be the hypotenuse. And it's going to represent then, we can say our overall velocity vectors really then are square root of Vx squared plus Vy squared. And that's going to then be 38 squared plus our 5.4 squared. We want to add those up and then take a square root. So that'll be 38 squared plus 5.4 squared. Oh boy, my calculator. Let me retry that, clear that. So 38 squared, I'm going to enter that, plus 5.4 squared. I'm going to enter that. I get 1473.16. I'm going to take a square root of all that. And I get about 38.4. All All right, so most of the velocity is based on its horizontal, but because it's got a small Vy at that point, it wasn't in free fall for very long, so we don't have a real big Vy, but when we Pythagorean those up, we get 38.4 meters per second. That'd be the overall velocity. Now the vector then requires us to measure an angle here too. So that would be theta right here, so we can take a tangent of theta, and that's going to be then opposite 5.4 over our 38. Make sure you're again your calculators in degrees, so we want to take a second tan 5.4 and divide that by 38. And I get there's my 8.1 degrees. 8.1 degrees. And in the fourth quadrant, that would be a negative angle, really, right? As we go around the circle this way. We really just have one more thing to do, and that's how far did the ball travel forward. So that, again, represents the range of the ball, and it's in CV. So for part F, we would say, well, how far does the ball go? Well, that's just Vx times t. Right? This would represent how far when the object's in free fall. When the object's traveling forward at a constant velocity. Okay, so we would say, well, how far? That's my kind of unknown. That's going to be my 38 meters per second times the time, but that's 0.55 seconds. So that'd be 38 times 0.55. And I get about 20.9 meters. Notice the distance between the pitcher's mound and home plate is around 18.4 meters. So the ball's traveling a little bit further than right to home plate. Right? We don't want the pitcher to pitch it onto the plate or right before the plate. They want to catchers kind of back a little bit. So that's going to be about 20.9 meters. Now, so there's 4 problems in this set. There's a couple more, but I'm going to let you guys work on that for one of your assignments, but I'll have the answer key there too for you. Does that make sense, kids? Okay, I hope you enjoyed this video. We'll talk to you later.